Start off by just reminding you, because sometimes we get lost after when we do lab in the weekend, kind of get lost about where we were in the notes, what exactly it is we cover. And that's why so every now and then in a longer chapter, I'll try to get you caught back up about what we're talking about here. This chapter's on bonding, okay, different kinds of bonds. All of this stuff, you don't have to copy it down. It's already there. I just summarized it. We talked about the three different kinds of bonds you can have, ionic, polar, and non-polar bonds, okay, between a metal and a non-metal or two non-metals, okay? And you know, ionic bonds, you had a difference between 1.7, polar covalent, non-polar covalent. They had their differences. You know, we talked about diatomic elements. And all that stuff, you know, we were able to do labs on it. We were able to do problems with it, electron dot notations and Lewis structures. Now, all of those probably make sense to us based on the octet rule. But there's a kind of bond I haven't talked about yet. It's going to be the next one. It's going to be C. A was ionic. B was covalent. Polar, non-polar. This is going to be C, metallic bonds. Okay, you can write that down. That's what we're picking up with. And this is one that doesn't make quite as much sense to us. All right? Metallic bond doesn't make quite as much sense. Let me explain. It makes sense if I take sodium and I react them with chlorine. You know? Chlorine wants one electron. Sodium wouldn't mind losing one. He drops to an octet. The octet rule says these guys would be very happy getting together and making salt. And they do. That's an ionic bond. This guy loses, gets a +1. This guy gains. That electron gets a -1, and that's an ionic bond. It also kind of makes sense when you get two guys who are both nonmetals and both want to gain. Like, for example, if I have a chlorine and another chlorine. These guys are really reactive. They're very highly electronegative, really want electrons, and they're so close they can taste it. They get one more electron, they would be very happy, right? They will have an octet. So it would make sense that they would form a covalent bond where neither guy could be told, and this guy's not going to rip it away from him, he's the same guy. He's the same exact strength. So they'll share them, and so we drew them. That makes sense. Both of those make sense because of the octet rule. But here's the weird part. One of the best bonds, one of the strongest bonds, one of the most important bonds, I should say, probably more than strength or best, most important bonds is the bonds that happen between metals, just a single metal. For example, you know, take any metal on the periodic table, take copper in its pure state, or silver, or gold, okay? I didn't combine them with anything. Just by themselves, they are a very strong bond. They're held together pretty well. What would cause that to happen? There's no real reason it would seem. Because those guys on the left side of the periodic table tend to lose electrons, right? Why? You know, you can understand a guy who wants to lose getting together with a guy who wants to gain. Made it happy. You can understand two guys who want to gain sharing. But two guys who want to lose, it doesn't seem to make sense. So I got to explain this bond. This is called the metallic bond. And this is the one that's kind of the weirdest and the strangest, but one of the most important ones to understand. Now, I actually showed you that first video on metals, on modern marvels. You're going to see another one tomorrow on metals. And both of them, you know, talk about the importance of the metallic bond. Now, I need you to understand the properties and all that other stuff about metals. All right, I'm going to explain those to you. Okay, so those of you just walking in, haven't missed a thing. I just kind of summarized on what we had done. This is where we left off C, metallic bond. This is where you are in the notes. All right, what is the metallic bond? Why would these guys, everybody on the left side of the periodic table, and you can think about these guys, everybody can envision aluminum foil. That's the aluminum bond. Everybody can envision iron and copper pipes, silver, earrings, gold, jewelry. You can envision how that bond's pretty strong. This metal thing I'm holding in my hand, I don't know what it's made out of, but they're strong bonds. All right? What is it that causes that bond? That's what I got to talk about today. I have a couple of animations to go along with this, and then a little short clip of a video that you're going to take notes on explaining the properties. Okay? So the metallic bond forms, and this is the weird part, between the same metallic element. So these guys supposedly all want to lose electrons. Why would they want to form a bond with each other? What actually happens when that, how does that bond get formed? Kind of makes sense. Two nonmetals want to get together because they both want to gain, so they'll share that electron or two. Kind of makes sense when a metal and a nonmetal get together. One guy wants to lose, one guy wants to gain. But a guy on the left side who wants to lose, still forms a strong bond with another one of his atoms and a whole bunch of their atoms. What forms that bond? I'm going to show you. Okay. Well, let's describe what the metals look like. We all kind of know this. Metals have very few electrons. They're on the left side. They have few electrons, and they're not held very tight. The outer shell electrons are held loosely. When they contact other atoms, they can lose them. Just a little bit of energy, and you can knock those electrons off. Those electrons are kind of, free to be kicked around, lost. So what happens when these guys a whole bunch of these atoms get together in a copper pipe or an aluminum foil, all right, or a steel girder? What happens is, just sitting next to each other, there's enough energy to knock off those electrons, okay? And they form, and this is much easier to see than it is to explain in words. I'm going to write it down, and then I'm going to show you a couple of little animations, pictures, and a video clip that are going to explain this better than the actual words do. But what happens is these electrons get knocked off, and they form kind of like a sea or a glue that holds together all those other ions that are left behind. Okay? The free electrons form a cloud or a sea of negative charge that act like a glue that hold the other positive ions together. Because when a metal loses his electron, he forms an ion, or an electron or two. Now, I have an animation first, which hopefully will work. It's one that has to go to the internet, and my connection here with this computer is being so old is not the greatest. If that doesn't work, it's okay. I've got the video that I can show you anyway, but hopefully this will work too. We have other things to write. I'm not done with the notes here, but just I want to show you the animation first before I go on. All right, I'll come back to this if you didn't get all that copied. I'm coming back to that in a second. Let me show you the animation first, if it works. Let's see. Turn that light off for me for a second. Okay, you ready? So here is your metal. Now I'm going to play it in a second so you can see what happens. Here's your metal sitting there, and these electrons, that because they want to be lost, they're so easily lost, they get knocked off just from the movement of the atoms kind of hanging out, being next to each other. And they form this sea or glue that holds all the other positive ions in this sea of electrons. And this is going to help explain. Look what happens to them when you put a charge across them. This is why we use metals for wires. They're going to carry an electric current very well. It's going to, the electrons are going to flow in one direction, be attracted to the positive side of the pole, and be repelled from the negative side. Okay? So basically, that's a little animation of what's going on at the molecular level, at the atomic level. Each of these guys ends up forming an ion, and the sea of electrons holds them all together like a glue. Now, I've got another clip of this, and the explanation, or I should say, the metallic bond explains all of the properties we think of when we think of an atom, or when we think of a metal. What do we think of when we think of it? I'm going to get to those properties right now. Hold on a second. I don't really want to quit out. I can just go back to this. What do we think of when we think of a metal? You can put the light back on. What are the properties of a metal? Shiny. That's going to be one of them. Don't have to write it down. I'm going to have them all listed here in a second. What else do we think of when we think? What else do metals do? They conduct. They conduct electricity and they conduct heat. That's two. And there's one other thing that metals do, and I talked about this in the video we saw the other day. This kind of illustrates it as well. What can I do to metals I can't do to a lot of other things? Yeah, I can bend them. That's called malleability. So those three things we're going to explain in terms of that metallic bond, okay? The attraction between the sea of electrons and those positive ions that are left behind explains the metallic bond and the properties of the metals. And those three properties we're going to explain, you're going to explain by taking notes on them on a little video clip from ages and ages ago, probably made before I was born. not exaggerating. I think I've shown this clip since the first day I ever taught anything. And I still show it. I mean, I think you could argue that I've updated my material pretty well over the years. But there are some things that just do a better job than others. If you look back at the lab back there, you see those old Mac computers, and probably some of you are wondering why. What could you possibly use those for besides paperweights? We don't use them for much in Chem 1. But we do, in Chem 2, we have one program that I've never found its equal in all the years I've looked. And I have looked. There are other programs that will do more than this program, but not as well and not as simply for a high school student to understand. So I keep them, and I still use them. When everybody got new computers around here and was throwing those other ones out, I said, give them to me. Over the years, I've had probably about 20 to 30 of those computers. Now, there's only about 12 left working, and when they go, that's it. But then again, I'll be done by then, too. But there's certain things that just show up better than others. So I'm going to show you a little video clip here. I want you to leave room, probably about 3 lines blank between each of these things. The three properties we mentioned. Leave yourself about 3 lines blank underneath each of those, and you're going to take your own notes on this from the movie. Okay, it's just not a whole movie. It's not like going to be an hour-long Modern Marvels. It's just a 10-minute clip you're going to watch. Okay. So copy all those down, leaving space in between each one. Okay? And when I start the video, you'll be able to see. You'll be able to answer those. All right? You turn that light back off again. Okay. I have a sound on, though. How old is this? This is very old. Seriously, I think it was maybe before I was born. See if there's a date on it anywhere. Still has a 3D effect,
that form our world are composed of atoms held together by powerful electrical forces we call chemical bonds.
Pretty impressive. Is there a date on there? Can you read it? My guess is the 60s. That's my guess. Maybe late 50s, early 60s. Great music, too.
Why do some substances drop and bounce? And some substances drop and break? And some substances just drop and stay there? Why do some substances remain solid as they're heated, while others liquefy quickly? And when substances interact, why is energy always required or given off? The physical and chemical properties of elements and compounds, to a large extent, depend on the nature of the bonds and weaker forces that hold their atoms and molecules together. Keep in mind, as we visualize atomic structure, that there is no way to show relative sizes correctly. The diameter of the average atom is 10,000 times as large as the diameter of its nucleus. If an atom were enlarged so that the goalposts of a soccer field passed through its outer limits, the nucleus would be no bigger than a pea, right in the middle of the field, about a centimeter in diameter. The interaction of the charged particles that make up atoms is the key to bonding. The attractive force between the positive charges of the protons in the nucleus and the negative charges of the electrons at various energy levels around the nucleus hold the electrons in the atom. When 2 atoms approach each other, there is an attractive force between the protons in the nucleus of one atom and the electrons in the other. All chemical bonds are formed in this way and create matter in its various forms. Elements, when atoms that are alike are bonded together, and compounds, when atoms that are different are held together by chemical bonds. Chemists have devised models for the different kinds of bonds, descriptions that help them and us to account for the properties of elements and compounds and to predict their behavior. The most significant kinds of bonds to chemists are those that form and break during chemical reactions. But it might be easier to understand their nature by first dealing with a type of bond that explains only the physical properties of one group of important substances. Our technological world, our high-tech world of complex structures and amazing devices, could not have developed without metals. In communications, construction, transportation, in the great electronic revolution, metals are essential substances and used in vast quantities. In all living organisms, compounds of metals are no less essential. Metal compounds are basic to many life processes.
What metals in blood?
In the periodic table of the elements, metals are all found in the same general area, and most of them have a number of similar properties that can be explained by the metallic bond that is found only between atoms of metals.
And explain them in terms of the bond.
This type of bond, like all bonds, is based on electronic structure. We can consider the structure of the metal, sodium, for instance, as a typical case. A sodium atom is electrically neutral. In its outermost energy level, it has one electron. This is called a valence electron. Valence electrons are involved in bonding. This single, highly energetic outer electron is so weakly held by the nucleus of its atom that in a great aggregation of such atoms, the effect is this. There is a sea of negatively charged valence electrons flowing among regularly arranged atoms that have lost their permanent outer electrons. This gives the atoms a positive charge, so we can call them ions. It's the attraction between the positively charged ions and the negative sea of electrons flowing between them that bonds all the atoms together to form the metallic elements. Under the microscope, we can watch metallic bonds forming as atoms of the metal silver arrange themselves into the very precise structure known as a crystal. A repeating pattern called a lattice is under construction. As the atoms move into the lattice, they free their electrons and become positive ions. The metallic bond can explain the similar properties of metals. Why do metals tend to have a shininess? Light waves are involved.
Luster.
Light waves have a certain frequency of vibration. They cause the sea of electrons on the outer surface of the metal to oscillate at the same frequency when the waves strike them. When this added energy is radiated away by the electrons, we see it as a reflection of light. The surface looks shiny. These mobile outer electrons, attracted to positive ions in all metals, also can account for many other properties that are...
I'll pause it for a few seconds. That's basically the electrons get energy. We saw that. We were giving electrons energy from, by making them jump up to higher energy levels. But remember, electrons are kind of like waves anyway. They're weird guys. And the fact that they are free-flowing in the metal, able to move, means that they will reflect the light from the sun, all right, which is basically energizing them, and reflect that back off of it. If they were bound tightly together, that wouldn't happen.
Characteristic of metals. When there's a voltage difference across two parts of a metal, the electrical force easily produces a movement of the free electrons. This accounts for the high electrical conductivity of metals. Metals are also good conductors of heat. Heat produces a high kinetic energy in the free electrons that are part of a metallic bond. Because they're highly mobile, they move and give up their extra energy to electrons with less energy. And these electrons pass their new energy on in the same way. For this reason, heat is easily conducted through a metal.
So again, it's the free-flowing electrons that are able to move. You saw that with the original animation I showed you too. Be attracted to one pole and repelled by the other. If they were all bound like they are in an ionic compound, where one guy gained, one guy lost, that wouldn't happen. You could not have that happen. You wouldn't have free-flowing electrons to do that. That's why we have our wires made of metals, because they can have free-moving electrons that can carry a current. They can actually move, the electrons can actually freely flow through there.
Metals are malleable and ductile. Under physical pressure, the lattices that form the crystals of metals will reshape themselves. Rows of ions in the lattice separate, slipping past one another. But as long as the separation is not too great, the attraction between the sea of electrons and the ions, that metallic bond, is strong enough to keep the metal from breaking apart. Instead, the lattice simply takes on a new alignment. The metal changes its shape without breaking. The metallic bond is pretty much the force that holds together our metal-based technological society. In metallic elements, all the ions attract all.
So again, the metal, the malleability has to do with the fact that those electrons can flow into the gaps that are created if you try to bend a metal, whereas that would not happen. And you're going to see a contrast to that with an ionic bond. Why is a salt crystal brittle? It breaks. Well, you'll see.
The electrons and the ions are all of one kind. In a second kind of bond, the attractive force is produced between ions alone, ions of different substances. When an active metal, like sodium, interacts with an active non-metal, like chlorine, the result is one of our most familiar compounds, ordinary table salt, sodium chloride. Like metals, salt forms crystals, and an X-ray of a salt crystal shows a structure similar to the one we see in metals, a lattice of regularly arranged parts. But there are not many similarities in properties. Salt crystals are clear and tend to bend light rather than reflect it as metals do. Salt crystals are very brittle. They shatter easily, not like metals. Does salt conduct electricity? No, not as a solid. Only when molten. And the boiling points and melting points of salts in general are relatively high. The melting point of table salt, for instance, is 800 degrees Celsius. This is more than 700 degrees higher than the melting point of the metal sodium, one of its constituents. The bond that holds these substances together is named for the kind of particle that forms them. It's the ionic bond.
Now, not only is this going to be a little bit of a review of ionic we already covered, but it's also going to contrast those same three properties, luster, malleability, and conductivity, why ionic bonds aren't like that. And it will hopefully make the metallic one a little bit clearer, too.
Formed by the force of attraction between positive and negative ions. The particles in a salt crystal are ions, as they are in metals. But the ions in a metallic element are all of one kind, and all positively charged. In salt and other ionic solids, this is not the case. We can see why if we consider what happens when just one sodium atom interacts with just one chlorine atom. A look at the periodic table tells us something about these atoms. Sodium is the first element in its period. Aside from the single valence electron in its outermost energy level, sodium has the electronic structure of neon, the noble gas, a highly unreactive element. Chlorine, on the other hand, is the next to last element in its period. It has 7 electrons in its outer level, just 1 electron short of the 8 that argon has, which is just as unreactive as neon. Now, as we bring the sodium and chlorine together with enough energy and close enough to interact, powerful electrostatic forces come into play. The forces move the single electron from the outer level of the sodium atom to the outer level of the chlorine atom, but with 1 less electron. The originally neutral sodium atom now has an excess of one positive charge. And the originally neutral chlorine atom, in gaining one electron, now has an excess of one negative charge. And so, both are ions, charged atoms. The two ions are held together in this ionic bond. This same force of attraction draws ion after ion into an arrangement that is very precisely determined by the electrostatic forces and the sizes of the ions involved. The ions pack themselves into a lattice, which gradually grows into an ionic crystal of table salt. The ionic bond can help explain the properties that we usually associate with table salt and other similar ionic compounds.
Now, we're going to contrast these to the metal, so pay attention.
Why are salt crystals transparent, not shiny like metals, which are also formed of ions? In the metallic bond, the free-flowing sea of outer electrons absorbs and then gives off the energy from light waves. But in ionic crystals, the outer electrons of both ions are bound tightly in the same configuration that the outer electrons of noble gases have. So the energy of light is not absorbed and re-radiated. Instead, light waves tend to pass through the crystals and make them appear transparent. Why is a salt crystal so brittle? When the crystal is stressed, the orientation of its positive and negative parts is changed. Positive ions were around every negative ion, and negative ions around every positive ion. But now, ions with the same charges come in close proximity to each other.
Okay, so now in a metal, you only have positive ions and a sea of electrons that can flow into the gaps. Here, you don't have that. There's no flowing sea of electrons that can make up for, compensate for that. When those two get together,
repulsion.
They repel.
Because like charges repel. And so the structure breaks apart. The crystal shatters. And as for electrical conductivity, even though all the parts of the salt crystal are charged, positive and negative ions, no charged parts are free-flowing, like the sea of electrons in a metal. They're all locked in place. So when a voltage difference is applied to the solid salt, there is no movement of charged particles. For the same reason, heat energy is not transmitted well through salt and other ionic substances in their solid phase. And boiling and melting points are high because ionic bonds, particularly between active metals and non-metals, are very strong.
What's that thing sitting on? And what is it? Crucible. It's got a handle. What's it?
When salt melts, the bonds that hold the ions together break, and the ions are no longer held in their rigid structure. Now a voltage difference has an effect. Free to move, negative ions in the molten salt are repelled by the charge on the negative electrode. Their movement toward the positive electrode constitutes a flow of electric current. But because ions are considerably heavier than electrons, they're more difficult to move. And so a molten ionic substance does not conduct electricity as well as a metal does.
All right. And the explanation is very simple. All right. The free-flowing electrons pretty much are the reason for all three of those properties. Because they're free-flowing, you could apply heat or an electricity or conductivity to it. Here's electricity, here's heat, and it's going to, those electrons can move, and it will carry the heat, it will carry or will transfer, I should say, the electrons or the heat or electricity. It's malleable because, look here again, I can bend this arrangement because the electrons can flow into any gaps that I make. All right, and light, it's shiny because, again, the light waves are going to hit those electrons, which can vibrate and reflect the light back. All right, so you should know that for the test because I'm going to ask you on the test. I ask you a short answer question on almost every test. And I think there are two on this one, and that will be one. One of them will be, it will simply say, explain luster, malleability, or conductivity in terms of the metallic bond. So you'll have to explain the metallic bond and that property together. You have to put the two together like you hopefully just did here, okay?